Hello, students. Fantastic evening. Hopefully you're doing well. Got some questions from 8-4. So we're going to take number 1 and number 5A. So number 1 right here, take a look at this equation. And so they've given us a graph of y equals mx plus 5. So as you look here, again, the slope is m. Okay, now m is a variable. We do not know what it is, but from looking at the graph, I can see that it is a downward slope. So I can tell you that m is negative. Remember, it's a variable. So we shouldn't have to write this because all that symbol means is the opposite. So when you see this one here, it doesn't mean negative slope. It means the opposite of whatever slope you had before. So when we take the opposite of something, we're now dealing with, if it was negative, it now becomes positive. If it was positive, it becomes negative. In this case, I can tell the graph is negative. If you're thinking, hey, they should have told me that that was negative, the answer is no. We should be able to say the value of the slope is some number and represent that with a cloud or a tree or a box or the letter M, because that way we're saying that we don't know the value of that, and that really isn't as critical here. If you really wanted to find it, you could find it by taking any 2 points and determining the ratio of rise to run. So that's perfectly fine to do that, but not critical for this. And again, if I say the slope is m, and I say, y equals mx plus b, I would say, oh, then the slope is positive. And if you say, yes, the slope is positive, you're going to get burned on the always, sometimes, never, because we do not know that, right? We do not know that the slope is positive for that. We just know that it's a number. Okay. Let's see here. What else do I have? And 5A. Okay, so 5A. Write each of the following equations in slope-intercept form and identify the slope and the y-intercept. Okay, well, you've got multiple ways to do this. It says first write it in slope-intercept form and identify the slope and the y-intercept. You can read the slope and the y-intercept from the graph. You can read it from the equation. It's completely up to you which way you choose to do it. So I will show a couple different techniques to doing this. Again, some of you may like one and not the other. So here is option number 1. If you had this equation, and make sure that's an x all the way through, equals 1, you could say, hey, I struggle with fractions at times. I'm going to multiply everything through by 12. And when I say everything, it's every term. So multiply the 1, the y over 4, and the x over 3. And now when you look at it, now you have 12x over 3 plus 12y over 4 equals 12. And the reason we do that is everything now simplifies. Okay, that seems not bad. I don't have to deal with fractions, perhaps. Maybe I feel more comfortable with that. Now you still have to get it in slope-intercept form, which means you have to get the y by itself. So get rid of the thing that is not a y, right? Simplify. What remains is 3y equals negative 4x plus 12. You could also have said 12 minus 4x, but slope-intercept form is y equals mx plus b, at least in this country. In other countries, it's a plus ax plus b or a plus bx, just so you know. That's just be aware of that. Not every student's going to come from the same place. All right, lastly, what I need to do is I need to get y by itself, so I'm going to divide everything by 3. You can choose to put a big bar over 3. I prefer, and I think you'll find it easier if you separate as if you were doing the distributive property and multiplying by 1/3. That seems to make it easier. I don't make the same amount of mistakes. So I end up with minus 4/3 x plus 4. Now it's slope-intercept form, and I can say my slope is negative 4/3, and my y-intercept is 4. Or you could write it as the point 0, 4. Okay, there's a technique. What is that technique? It's the I freaking hate fractions technique. And I hope that you've throughout this class been like, actually, I'm not so upset with fractions. Okay, so there you go. That's one way to do it. Typically, students are like, hey, show me another way. Maybe I'd like the other way better. Perfect. We can do that. Okay, so now option number 2. Here we go. Number 2. Number 2 says, I am okay with fractions. I'm okay with those. I still need to get everything to one side, so I'll just write out the equation. Y over 4 equals 1. And what I'm going to do here is I'm just going to say, yeah, the fractions are fine. Let me subtract x over 3 from both sides. Okay. And what comes next is, now this one's gone, so I have y over 4 equals minus x over 3 plus 1. Cool. I am almost done now. I just need to get y by itself. The only thing stopping it is somebody divided by 4. So I need to multiply by 4 and make sure I do that on both sides to balance it out. And let's see what we get. We get y, and y equals negative 4x over 3 because I distribute to each one, and I get a plus 4. And at this point in time, I am done. It's in slope-intercept form. The slope is 4/3. The y-intercept is 4. And there you go. I know, that's pretty cool. It's not bad. Once you get used to fractions, it can actually save a few steps. So if you want to take a look, the one on the left looks like I multiplied everything, then I had to simplify everything, then I had to subtract everything, and then I had to divide everything. So 1, 2, 3, 4 steps on the right-hand side. It took 2 steps if you feel more comfortable with fractions. So you hopefully can see there's a reason why it's helpful. If you don't want things to take as long, maybe learn a little bit more about the fractions, feel more comfortable with them. Hmm. Is there any other way to do this? Probably. You could probably generalize this if you wanted to, right? Like if they, because I'm sitting here looking at it, I'm like, oh my gosh, this is one where I might, anything that looks like x over a plus y over b equals 1, and I'd be all over this with, let me tell you what the slope is. I can do it in general. And that's why the idea of proofs is so powerful to mathematicians. Okay, we are clever but lazy. Okay, we're looking for things to be more efficient. So if I was saying, if you're like, hey, I don't even know what you're talking about. What do you mean be more efficient? If you gave me another problem later, right? And you said, Scott, what about x over 7 plus y over negative 2, and that equals 1? Can you find the slope and the y-intercept? I could still go over here and do the same 2 steps and get to the end, right? But if I stop and I say, wait a minute, let me generalize x over a plus y over b. Could I generalize this? So now watch, when I do that and I bring the x over a to the other side, it becomes negative, right? So I'm going to bring this to the other side by subtracting. So now I have y over b equals negative x over a plus 1. Now multiply everything by b and take a look at what you get. If you multiply everything by b, you get something where you could read it off. This is why I love generalizing. I end up with y equals negative b over ax plus b. Okay. Is that cool? Because to me, that's super cool. Negative b over a is the slope, and the y-intercept is actually the value of b, which is the thing under y. So if you gave me a different question and you said, Scott, look at this one, and you gave me this one, you're like, I see a pattern here. Why don't I just solve it in general? Then you can give me whatever you want for the a and the b values in that function, and I can create very quickly the answer to it. So I could now look at this. This is why sometimes people think mathematicians are like free. Oops, wrong tool. Sorry about that. Are freakishly good. Yeah, I say freakishly good as I choose the wrong tool. Okay, forget about that. All right, so down here, if you gave me this problem, I could say, okay, well, I know my m is going to be negative b over a. Got it. So my slope is going to be 2/7, and my y-intercept is going to be -2. I'm done. I'm done with the problem. You're still in the middle of solving it. Okay, I could come up here and do the same thing. I could say m equals negative b4/3. Done. And the slope, or sorry, the y-intercept is just what's under the y value. It's 4. Done. Anything else? I mean, we could make it more complicated, right? Right? Somebody could do a whole bunch of crazy stuff to it, but it doesn't matter. You've generalized, so now it doesn't matter to you. It's going to be fantastic. You'd be great. Okay, enough with that. Enough with that. People are asking, how can I solve this efficiently, or what's the quickest way? The quickest way sometimes is to generalize, and then you could solve a million of those problems, and it'd be all take the same amount of time. Okay, let's look over to Math Connections. We have 8, 9, and 12 as part of the request. So 8, 9, and 12 Math Connections. Here we go. Math Connections 8. Student asks whether the slope of a line is related to division by 0. How do you respond? Draw a vertical line on a graph. Go to a graph, draw a vertical line, right? And then find a couple of points on that line. I don't care where you find your vertical line. Find a couple of points. Then use those points to determine the slope. And I think if you do that, create actual numbers, go and do that, find the slope. I think you'll be able to see how this is related to division by 0. I'm not going to go through and do that one any more than that. That is a huge push in the right direction. I feel like we got you down the right track. 8, number 9. This student. Okay. Well, so student added 5 to both sides. You can see they added 5 to both sides. That looks good. And then did a little simplifying. So I guess my question would be this. What is 3x minus 3x? Right? 3x minus 3x, 0, right? What about 12x minus 12x? What would that be? Yeah, 0. Okay, so now what if I said this? What if I wrote 5 minus 5x? Is that following the same pattern? Like with 5 minus 5x, can I just pretend that there are parentheses there and do this part first? Check that portion as you look at this question to see how you might help Jonah. All right. And I think the last one was 12. Yeah. Okay. Let's see here. There's 12. And 12 says, Jackson says the equation is a linear equation. What is your response? Let's see here. Well, the definition of a linear equation in your mind, maybe many things, but what you really want to go back to, if you want to, the definition, they did say that you can have a linear equation as something that can be written as ax plus by equals c. Okay. You could say, okay, that's a linear equation. So in one sense, you could, if you keep your definition that broad. However, what we really want when we do a linear equation is we want to be able to graph a line, right? So let's come over and put some points in here and see what happens to our graph. Again, we want to graph a line. In our minds, that should be a linear equation. So if you have this 0x plus 0y equals 0. Let's put in some points. Pick a number for x, any number you want. Okay, 3, good. Okay, so you pick 3 for x. Now plug in a number for y. Okay, so I'll put 3 in for x. 5, okay, 5 for y. So put in 5 for y. Now I have 0 times 3 plus 0 times 5 is supposed to equal 0. Does that equal 0? Yeah, it does equal 0. So this point is a solution to the equation that's listed here. Okay. Let's see here. Let's do another one. So instead of 3 and 5, let's pick some other points. Why don't we pick 2 and 4? So if I put 2 in for x and 4 in for y, is 0 times x plus 0 times y, is that going to equal 0? And you'd say yes. So 2 comma 4 is also a solution. These are the solutions. Now in the most part, when we graph them, if we graph a linear equation, when we graph them, we should get a line. Okay, so let's check. I have the point 3, 5, 1, 2, 3, 1, 2, 3, 4, 5. There it is. Next one is over 2, up 4. Okay, there we go. So down 1, left 1. All right, let's try another point. Maybe 1, 3. Let's check it. Plug a 1 in for x. That gives you 0. Plug a 3 in for y. That gives you 0. You add those together, you get 0 at the end. And the next point I would put down is 1, 3. And right now, maybe you're busy thinking like I might be thinking, holy cow, this is a linear equation because I can fit, I've got to grab this tool because I can't draw that. I can fit a line right on top of it. Look at how fantastic that is. Oh yeah, this looks like a linear equation. All right, well, let's try some other points. Let's try the point 1, 4. I plug in 1 for x, I plug in 4 for y. And you know what? This also works. So 1, 3 works, but so does 1, 4. And so does 1, 5. And so does 1, 6. And 1, 7. And 1, 8. And 1, 9. And 1, 10. And 1, 11. And 1, 2. And 1, 3. And 1, 1. And 1, 0. And 1, negative 1. 1. All of those work. And so does 2, though, right? We said 2, 4 works, but so does 2, 3. And 2, 2. And 2, 1. And 2, 0. And 2, 5. And 2, 7. And 2, 8. And 2, 9. And 3. And okay, what's happening here? Every point that you pick for x, every point that you pick for x and every point that you pick for y, guess what? This is true. Because anything times 0 is 0. And if you add 0 plus 0, you get 0. So basically, you can't say that this is always going to form a straight line. I drew a line between the first 3 points, but as it turns out, I could have picked a bunch of other points, and I got some crazy graphs going on as I try to connect all the dots. And those are only the whole number dots. Couldn't 1.5 and 2.3 also work? When I multiply by 0, I get 0. So now I get every number in here. So I'm going to shade all of the solutions here. I think you're going to like this one. Okay, are you ready? I'm going to shade them all in green. And here they are. Yep. Every single point on the coordinate plane is a solution to that equation. So if you think that this looks like a line, then you would say, good job, Jackson. And if you look at that and say, Jackson, I think we may need to chat a little bit. There might be something else to this that you are missing. And that is how I might nudge you in the direction on number 12. Okay. Phew. All right. Let's see here. I'm going to talk very briefly about a few of these components because some of the terms I think get people going the wrong direction, or people just overgeneralize. So I'm going to talk about this term simplify. And I'm going to talk about this one, solve. These terms, typically, you're not going to see those together. You simplify an expression like 3 times 5 plus 1 over 2. You could simplify this. We would not solve this. Solving is resolved for things like equations. So we reserve this term of solve for that. Like 3x plus 1 equals 16. I could ask you to solve this equation. Now, without anything else, it may be challenging to say, what am I solving it for? In this case, there's only one variable, so the implication is you would solve for x. That means get x by itself. If I gave you an equation like y plus 2x equals 3, and I said solve, you should say to me, what do you want me to solve it for? And I could say, oh, solve for y. That means get y by itself. Got it. So then you subtract the 2x from both sides, and you suddenly have slope-intercept form. That is solving for y. You could have also said, wait a minute, solve for x. That means get x by itself. In which case, I'd get the y to the other side and then divide by 2. Okay. So each of these, like the same equation, each of them use the word solve, but I have to know what I'm solving for. So if someone says, okay, I'm going to solve negative 5x plus 2y equals 7. Okay, I'm going to solve that. Well, that's awesome. But I can tell you one thing you're not going to do is you're not going to end up with x equals 2 here because you've got another variable. You're going to have an answer that involves a y if you're going to try to solve for x. Now, someone could say, plug in, like here when it says solve for x, right? They could say, put in y equals 7 and solve for x. Now plug 7 in for y. You only have one variable, solve for the x. So be careful with that. Students often use language like that. They will say it. You might buy into it. And now what, right? Now you're looking at them saying, oh, well, go ahead and show me. Like in, let's see here. Like in question 9, Jonah tried to solve the equation. Like the first thing, every time I read these questions, the first thing I would say is, okay, he's going to solve an equation. For what? What is he solving for? That would be my first question when I do this one, right? So anyway, as you go through these, make sure you're understanding the terms. Make sure that your pretend student, and I know they're fake students right now, but honestly, it's probably good that they're fake students because we're still learning the concepts. If they were real students and we didn't have a foundation in the concepts, we'd end up just like all the other teachers in America. So we're not going to be like that. We're going to be better. And that's what I want you to think about. If you think this is solved, then if you plug it back into the original, it should be true. And that did not happen here. So be very careful as you go through these. And again, just like with everything else, if you have other questions, please let me know. Hopefully this helped work, get you on the right track, and I'll see you soon in class. Off you go.